Welcome back to my lectures on groups, rings, and fields. Our next topic is on 3 isomorphism theorems on groups. And one of them we already established earlier. The first one that we established is this. First isomorphism theorem. So I'm not going to prove this theorem, but I'll state the theorem and I'll give you the example. So let phi is a homomorphism from G to, you can be a group homomorphism with the kernel K. So that means kernel K is a normal subgroup of G. Then let gamma from G to G over K factor group, because it is possible because the K is a normal subgroup, be the canonical homomorphism What will be the definition of this? Gamma of G is equal to Gk is equal to Kg. That is a canonical homomorphism. Then there exists a isomorphism from the factor group to the image of G such that, so what will be the diagram? G prime, this is phi, and you have a G over K. K is the kernel of this. This goes like this, and G over K is gamma, and this is our mu. So, such that phi of G is equal to mu after gamma of G for all G in G. This is the theorem we established earlier. So let us do an example here. Let us say G is equal to Z4 cross Z2, and that goes to C4, and so this is our G prime by phi of xy is equal to x. So this is definitely a homomorphism with the kernel K is equal to 0 times C2, because all the elements of this goes to the 0th element of 4. So we have, what we have is Z4, Z2, then here it is actually Z4, and the kernel actually will be Z4 times C2 over Z2, because this is actually isomorphic to Z2. This is nothing but Z2, and that is nothing but, this is actually nothing but C4. So this is our G over K. So what we need to show that is the image of phi, the image of phi, so the image of G is equal to, image of Z is what? Image of Z4 times Z2 is equal to, this is actually a onto map. So phi of Z4, Z2 is C4. And this, so phi of C2 is C4. So this is the image of phi. So we need to show that phi of G is isomorphic to G over K. What is G over K? G over K is Z4. This is, because it is onto, it is Z4, and because K is equal to 0 cross Z2, the factor group is also going to be C4. And that is what the theorem says. So this is the first theorem, and we have already done the proof of this theorem earlier. So before we come to the next theorem, we need a couple of sub-results. So let us start with the first sub-result that we need to establish the second isomorphism theorem. So let N be a normal subgroup of G and gamma be the canonical isomorphism, canonical homomorphism from G to the factor group G over N. And let L be the collection of all normal subgroups of G containing N. N is a normal subgroup of G and N contains L. L is normal in G. And K is equal to the collection of all subgroup of the factor group. H is a subgroup. Then the map from phi L to K by phi of L, let this call just H. I think that makes sense. H. By L is equal to gamma of L. See, the gamma is defined from G to the factor group. So this is actually defined by all elements from this is actually defined by gamma of L, where L belongs to L. So this map defined by the E is bijective. So we'll start with an example here so that this result is very clear. Let us take G is equal to Z and N is equal to 6N, 6C. So definitely this is a normal subgroup of G. And what is G over K? G over N? That is 6C over 6C, and that is nothing but C6. And that is 0, 1, 2, 3, 4, and 5. So, what is gamma? Gamma is from Z to Z6. Okay. Now, what is L? Is a collection of all normal subgroup of G containing 6C. So that is actually 6C, 3C, 2C, C. Right? These are the only normal subgroups containing 6C. See, all the subgroups of C are NCs and it should contain this. So these are the only ones. And what are the subgroups of Z6? Subgroups of, okay, that is actually our K is equal to subgroups of this. This is our G over and all subgroup of Gn. So what are the subgroups of this? One is 0, then 0, 2, 4, then 0, 3, then 0, 1, 2, 3, 4, 5. These are the only subgroups. So we have 1, 2, 3, 4 elements here, and there are 1, 2, 3, 4 elements here. So the definition of phi will be phi of Z will go to, or phi of 6C, let's start with phi of 6C. Phi of 6C is our 0, because that is a kernel and it should go to the 0th element here. And phi of 2C will be, or phi of 3C will be 0, 3. Phi of 2C will be 0, 2, 4, and phi of Z will be the whole of C6. So this is actually a one-to-one map, and that is what exactly what we are going to show here. So the first part of the proof is phi is 1, 1. So let L belongs to the collection of all subgroups of normal subgroups of G containing N. This implies N is a subgroup of L, and that implies Xn is a subset of L for all X in L. Because L is L contains N, so this is true. And this implies gamma of Xn is contained in gamma of L. And this is actually the element of a subgroup of G over N, and that is contained in here. And when X runs through all L, this will become gamma inverse of gamma L is equal to L. When this goes through all X, this will be L. So this total will be gamma of L. So gamma inverse of gamma L will be L. And that means gamma inverse of phi of L is equal to L, because this is actually gamma of L. So let L comma M belongs to L, and phi of L is equal to phi of M. And that implies gamma inverse of phi of L is equal to gamma inverse of phi of M. Because these two are equal, so I am taking the gamma inverse from both sides. And this is L, and that is equal to M. Which means that phi is 1. And next one is phi is on 2. For that, what we need to do is, we'll say let H be a subgroup of G over N. And that implies gamma inverse of H is a normal subgroup of G. So H is a subgroup of this factor group, meaning the elements of H are the cosets of N including N, because N is the identity of this factor group. So this also implies N is an element of H. That means and gamma inverse of this subgroup, this is a subgroup of G over N, and I am taking the inverse of that, that is equal to N. Because this is the identity of this group, and if you take the inverse of that, it should be the normal subgroup. And this implies that N is a subgroup of gamma inverse of H, because H contains N, and one of the element is this. So the whole of N will be the subgroup of gamma inverse H. Okay, so gamma inverse H is what? Gamma inverse H is a normal subgroup of G. So that means this gamma inverse belongs to L. And that means gamma inverse of H is in L means it is a normal subgroup of G containing N. So that means gamma of H is equal to H there. Now probably this is more precisely, this will be gamma inverse of H is equal to H, and that means there exists an element gamma inverse of H in L that is mapped to H implies phi is onto. We need to find out for every H in G of N, there exists an element in L that is mapped to that, and that's exactly what we did. So before going to the next sub-result, we need one definition. So let H and K be subgroups of G. Just a subgroup. It is not need not be normal. Just two subgroups of G, and define HK by HK. These are from element from H and K from K. So this HK doesn't need to be a subgroup of G, especially when G is a non-abelian group. Doesn't need to be a subgroup. Now define H join K, join of H and K by the smallest subgroup containing smallest subgroup of G containing H. Now, my claim is, that is next lemma, if H is a subgroup of G and N is a normal subgroup of G, then the join of H and K is equal to H and N is equal to Hn, and that is equal to Nh. And if H is normal, then the join is a normal subgroup of G. See, this is the smallest subgroup containing Hn. So this doesn't need to be a normal subgroup. In normal cases, like in any, if you take any subgroup H and N, this doesn't need to be a group even. So we are so if N is normal, then this will become a subgroup, and that is equal to the join of H and N. So the proof goes like this. Since H join N is the smallest subgroup containing Hn, it is enough to prove that Hn is a subgroup when N is normal. If this is already a subgroup, then that is the one we are looking for here, because this is the smallest subgroup containing this. So what we do is, let H1, H2 belongs to H, and N1, N2 belongs to N. So we'll see, we need to show that this is a subgroup. That means we need to show that it is closed under the binary operation, and this has got the identity, and for every element there is an inverse. So let's see whether this is closed. So H1, N1, that is the first element of this group, times H2, N2, that is the second element. We need to show that this also belongs to Hn. This is equal to H1 times N1, H2 times N2. We can regroup that because of the associativity. Because N is normal, when N is normal, for all G belongs to G and N belongs to N, Gn is equal to Ng. Sorry, for all G belongs to G and for all N belongs to N, we can find n1 g. There is an element in n, that is n1, that is equal to this. So here this means that h1 we can find an n3 such that n1 h2 is equal to h2 n3 n2 for some n3 in n, and that is equal to h1 h2 times n3 n2, and that belongs to h, because this belongs to h, this belongs to n, and that implies Hn is closed. And E is equal to E times E, so that definitely belongs to Hn. And let us take an element, let NH belongs to NH. Sorry, Hn belongs to Hn. We need to find out the inverse of this also belongs to this. This implies Hn inverse is equal to N inverse H inverse, and that is equal to H inverse some n1 for some n1 because n is normal. For same reason like this, and that implies this belongs to, that implies Hn inverse belongs to Hn, and that implies Hn is a subgroup, and that implies H join n is equal to Hn. Similarly, we can show that, replace n with h and h with n, can show that h join n is equal to nh. So this part is done. Now if h is also normal, then this is a normal subgroup. How do you show it's a normal subgroup? For all G in G and H in H, G inverse belongs to H. So we need to show that instead of H we'll have Hn. So Hn, when H is also normal, then G Hn G inverse is equal to G H G inverse G and G inverse, because I'm adding G inverse and G. This is actually identity in between these two, and that is equal to G H G inverse G and G inverse. Since both of them are normal, this belongs to H. This belongs to H and this belongs to N, because H and N are normal. And that implies Hn is normal. Now we are ready for the second isomorphism theorem. Second isomorphism theorem. So let H be a subgroup of G and N is a normal subgroup of G. Then Hn over N is isomorphic to H over H intersection N. See, when H and N are subgroups, H intersection N is a subgroup. When N is normal, Hn is a subgroup. So the whole statement makes sense. Only when N is a normal subgroup of G and H is a subgroup of G. So let us start with the first isomorphism theorem. So since N is a normal subgroup of G, then gamma from G to G over N is a canonical homomorphism with the kernel N, because the identity of this subgroup, this group is N. So it is the subgroup of G that is mapped to the identity, and that is N. So we are making use of this homomorphism to establish this result. Okay, see, let us start from here. H is a subgroup of G. So now we are going to restrict this gamma to H only, meaning we are not taking every element of G, but only those elements from H. So we call it as gamma H. That is actually from H2 gamma of H. The kernel of this homomorphism is N. So the kernel of this homomorphism will be H intersection N. So we have a homomorphism here with a kernel, and that implies H over, using the first homomorphism theorem, H over the kernel is isomorphic to, this is our phi, so phi of h, and that is gamma h. So this is our first result. We are using the same thing again. Hn is a subgroup of G. Now instead of H, we restrict Hn. And that is from Hn to y of Hn, and that is same as y of h, because y of h is the identity of this. So every element of h, every element of n goes to the identity element of g over n. So y of hn is equal to y of h times y of n, which is n is actually identity of this, so it is actually y of h. So again we will apply this rule, the first theorem, and that implies Hn, or with the kernel, so with the kernel is going to be n. So here this will be Hn over n is isomorphic to gamma of h again, and this is number 2. So when we combine these two together, this is isomorphic to gamma of h, this is also isomorphic to gamma of h, so this is isomorphic to this. So that implies from 1 and 2, h over h intersection n is isomorphic to hn over, and that is a second isomorphism theorem. Now we found that these two factor groups are isomorphic. So let us find the isomorphism, the function, the real function which goes from here to here or here to here. So for that, what we'll do is we'll take this one as mu1 and this one as mu2. So mu1 is from h over h intersection to gamma of h, mu2 is from hn over n to gamma of h. So gamma of h is here, and you have h over h intersection n, and that is our mu1 and we have mu2 here, and that is from hn over n. And we need to find out a map like this, for example phi. So mu1, this is an isomorphism, so mu1 inverse exists. So mu1 inverse goes from here to here. So mu2 after mu1 is going to be our phi. So phi takes an element from here. Element from here is actually hn n. is equal to mu1 inverse mu2 of h and n. Mu1 inverse is going from here. So this goes mu2 goes from here to gamma of h, and mu1 inverse from here to here. And this is actually equal to mu2 of hn. Mu2 of hn, this is going to be mu inverse of hn, because this is n belongs to n, so this will become n. And where is this h? H is in the intersection of h and n. So that is going to be NH of H intersection N. See, there is an N here, it is silent, and that is actually merged with this capital N. This is the identity of G over N. So, Hn of N, the image of Hn of N is going to be, this is Hn. Hn of H intersection N. So that is the explicit definition of this isomorphism.